This is our video for Unit 7, Day 6. We're going to be talking about polynomial rational functions, finding the end behavior, and also finding the domain for polynomial rational functions. So first thing we're going to do is talk about what polynomial rational function means. So polynomial, seen this word before. This means integer powers. Rational is another one we've seen before. Means fraction. So that's basically what a polynomial rational function is. It's a rational function made of two polynomial functions. So something looks like polynomial over another polynomial. So just a notation saying we have two polynomial functions and it's a quotient of those two, so rational function. So fraction, rational function made of two polynomial functions. So using this notation, we refer to the highest power on the top as n and the highest power on the bottom as m. And we're going to observe there's some different end behaviors that occur based on which one of those two is bigger or if they're the same. So that's the first thing we do with these polynomial rational functions is look at their end behavior. So end behavior means what is the function doing as x gets larger and larger and larger, x goes to infinity. So for a polynomial rational function, there's three options we have. So one of the options we could have is horizontal asymptote at y equals 0. So get closer and closer and closer to the x-axis as x goes to infinity. And this will occur if the power on the bottom of the function, polynomial degree on the bottom of the function, is greater than polynomial degree on the top. So for notation from the first slide, that would mean m is greater than n. So the bottom function will go towards infinity faster than top will. So overall, the fraction will get smaller and smaller and smaller as we put bigger numbers in. And that's what will drive it closer to 0. Second thing is we could have a horizontal asymptote that's defined by the leading coefficients. And this will happen if we have the same degree polynomial on top and bottom. So if m equals n. And then our third option is we could also have no horizontal asymptote. So we have this function just either growing larger and larger, larger, or smaller and smaller, not getting closer to any number. So no asymptote, and that's if the degree on the top is greater, it'll go to infinity faster than the degree on the bottom, so it won't be moving towards a number or getting smaller, it'll be growing. So how do we determine the end behavior for these polynomial rational functions when they have so many different terms in them is we only look at the dominant terms. And what that means basically the terms that will dominate this function, control the numbers more as numbers get larger and larger and larger. So what that really means is just the leading terms. If we're putting in really, really big numbers, x is going to infinity, x to the 7th or x to the 3rd or x squared or x or just a constant number like 197 doesn't have as much effect as taking that same number and raising it to the 8th power. So that's my dominant term on the top. Same thing with the bottom. All right, x to the 4th or x or negative 3, it's not going to have the same impact as taking a number raising it to the 11th power. So to find the end behavior for this function, we're really just looking at is the dominant terms, 3x to the 8th over x to the 11th. And then from that, we're looking at which powers are greater. So the top function has a degree of 8. That's what we're calling n. The bottom polynomial function has a degree of 11, m. So m is greater than n here, by meaning the bottom will grow faster than the top. That will make the whole thing as a fraction smaller and smaller value as x gets larger. So we have a horizontal asymptote at y equals 0. So this function will get closer and closer to 0 as we put in larger and larger numbers. Alright, we got two more here just to illustrate how this works. So starting with one on the left, again, we only want to look at the leading terms, the dominant terms. So on the top, that would just be x to the 3rd, highest power term. Same thing on the bottom, just look at x squared. As we go to infinity, x squared will dominate this a lot more than 500. Same thing with the top. X to the 3rd will dominate the top a lot more than x squared or a constant like 3. So we're going to think about this in terms of 5x to the 3rd over x squared. Again, we look at our powers, n on the top, m on the bottom. In this case, n is greater than m. So our degree on the top is larger, so it's not going to be getting smaller. It's going to be getting larger and larger because the top will be growing faster than the bottom. So in this case, we have no horizontal asymptote. And moving over to on the right, it's going to be the same idea. We only look at the leading terms. They will dominate the behavior. So we're looking at 5x to the 6th over 6x to the 6th. So we have the same power, same degree terms in both functions. So n is equal to m. And in this case, we define a horizontal asymptote using the leading coefficients. So we have a horizontal asymptote at y equals 5 over 6. So the last thing we're going to talk about is finding the domain for a polynomial rational function. How we determine the domain for a function. So the main thing to remember is that anywhere the denominator of the function is 0, that value will not be in the domain. So if we find the zeros as the denominator for a polynomial rational function, that will tell us values that are not in the domain for the function. These are called points of discontinuity. Points of discontinuity, they're breaks in the domain. So the way we find the domains, we see where this function is not defined. Where is there 0 in the denominator? So find zeros of this denominator. So here denominators are quadratic, so we can solve this one by factoring. And we get two values here to exclude from the domain, -3 and -1. So from this we can already define the domain. We're going to exclude everything, and we're going to exclude -3 and -1. We're going to include everything else. So we'll go from -infinity up to -3, not include -3, go up to -1, not include -1, and go up to infinity. Another thing we can do with these these 2 points of discontinuity is classify them. Points of discontinuity fall into two categories. So one is vertical asymptotes, like we've seen in our rational function and our log function. And the other is called a removable discontinuity, or a hole in the graph. So the way we do this, classify them, is we look for any common zeros that the denominator has with the numerator. So we also, at this point, look for zeros in the numerator. So it's also quadratic, also factorable. So here we get two solutions of -3 and -2. So these are the two zeros for the numerator, and they have one in common with the denominator, and that's -3. So this is called a common zero. It's a zero they both have in common, and that means there's a hole in the graph. At -3. Instead of an asymptote, there's a hole at -3, which means that at -1, since it's not a common zero, -2, -1, it's not a common zero, that's going to be a vertical asymptote. So if you ever see directions that say classify points of discontinuity, that's what it's saying to do. Is it a vertical asymptote, or is it a hole in the graph? So last thing, more generally talk about how we find domain for functions. Something we've been doing as we look at how transformations affect our different parent graphs is there's really three big things we always look for. And one is what we just talked about. We look for 0 in the denominator. So anywhere we're dividing by 0, obviously we can't do that, so that will be a point of discontinuity. That will be something we have to exclude from the domain. Another thing is we have a radical function if we see a negative under an even root. right? There's no even roots of negative numbers. We can't have square root of a negative number, because no number multiplied by itself will give you a negative number. So that's another thing to look for, is any even root. So square root or fourth root or sixth root, any even root, negative sign under there, you'd have to eliminate any from the domain. That would make that argument negative. And third thing with the functions we've talked about so far is anything that would make a 0 or negative number in a log. Right, we can't raise anything to any power and get back 0. So that's not going to be something we can put in as an argument for a log function. So if you're looking for more examples for what we've done in this video, you can look at, search for polynomial rational functions. In behavior, and also finding domain of functions.